Hmm. Myself, Dr. Amjad Ali, Assistant Professor, Department of Chemistry. Today we will discuss about the importance of chirality and methods of chirality inductions. Before going to the point, we will first ask few questions and we will answer them accordingly. So let's start. The points to be discussed today are: what is chirality, why is it so important and demanding, and how are the different methods employed to induce chirality in the prochiral molecules. Before going to that, we will discuss about some importance of the chirality. Importance of chirality, to know that how why this is so demanding and so important in the biological systems. First of all, we will see that thalidomide. Thalidomide have R and S forms because of one chiral centers. Yeah, they are non-superimposable mirror images. Earlier, it was used to racemic mixture of these molecules was used to treat the pregnant women for their sleeping sickness. But later, it was found that the only one form of thalidomide, one enantiomer of thalidomide are effective for the treatment of sleeping sickness of women, while the other affected badly. So in that way, that the children born were under mature, there some children were born without hands, without legs, because that this form was created some mutation, and the children were born like that. What happened here, that this chiral center binds uh, with that R1 is bound in the biological system that treats the sleeping sickness of a woman, while the S form binds with the biological system and creates mutation that causes that problem. In another example, you will see that a- asparagine. Asparagine have the enantiomer R and S. We will see that the R asparagine are sweet in taste, while S asparagine is bitter in taste. So the orientation of this group in the space has affected the change the taste of this molecule. In another example, you will see that ibuprofen. Ibuprofen has S and R enantiomers, and this ibuprofen have um, effects, different effects in the biological systems. We will see that the S enantiomer is used as an anti-inflammatory and analgesic, while the R enantiomer has no effect on in the biological systems. So in another example, we will take the alpha tocopherol. In alpha tocopherol, there are three chiral centers, uh, three chiral centers. So there can be uh, four enantiomeric pairs. In these four enantiomeric pairs, we will see that RRR and SSS enantiomeric pairs. You will see that you will see that 100 per RRR enantiomeric pair show 100% activity, while SSS is only 60% activity. In another case of RSR and SRS enantiomeric pairs, 50 RSR shows 57%, while SRS shows 37% activity. Similarly, RRS and SSR enantiomeric pairs showed 90% and 21% respectively, while RSS, RSS and SRR in ansomeric pair shows 73%, 31% activity. This From this activity, we can clearly conclude that the spatial arrangement of the atom is very important in the biological system for their binding and their activity. So this answers our first question that why it is important and demanding. In another case, we will see that the types of chirality. In types of chirality, first we will understand what is the chirality. ठीक है? Chirality is an spatial arrangement of atoms of group around the central atom or in the molecules that imparts the optical activity that makes the molecule optically active, and that optically active molecules change the activity of biological systems. Here we will try to understand that this we will see the one and one dash. These are the uh, mm, one and one dash are mirror images of each other. We will say that uh, non-superimposable mirror images. that these two are enantiomers, non-superimposable mirror images. That if you see that this is the carbon center, then attached with the four different atoms. This is the sp3 carbon because four different sigma atoms are attached with the sigma bond. So this chiral center has uh, has the ability to uh, to rotate the plane polarized light. So these are both are optically active uh, molecules, but they are several molecules. They are not sp3 carbon, but they are optically active. We will see a few examples of them, like allenes. Allenes, we will see that there is a sp carbon, and these two groups are in plane. These two are, one is below the plane, one is above the plane, and their mirror images are non-superimposable, so both are optically active. And in the similar way that aspirants, we will see that two cyclic groups are attached with a single atom that form the aspirant, and here the groups attached here are in the plane, and these two groups, one red is below the plane while blue is above the plane, and their mirror images are non-superimposed. So those two are also optically active molecules. In the third example of birals, we will see that two phenyl groups attached with a single bond that can rotate through this single bond. But if we attach at the ortho position the two bulky groups, so that the rotation can be restricted, and the groups present in the ortho position of two phenyl groups can be restricted or arrested in the one side, and their mirror images are the enantiomers, non-superimposable mirror image becomes, and this becomes optically active and rotates the plane polarized light. In another case of the helix is helical structures are that in such a way that rings are arranged that in after 5 to 6 rings attachment that becomes a helical shape, and these helical shapes also rotate the plane polarized, and so the chirality. Here, here is this. All the examples have the axial chirality. Axial chirality in this allene, in aspirants, in biphenyl, biryls, and in helix. All four show the axial chiralities. And to understand a drop is isomerism, here in this case in biaryls, that signal bond chirality is induced due to the restrict rotation of the single bond is called atrop isomerism. In another case, we will see that the methods of chirality inductions, how the chirality in the molecule is induced. So there are several methods, and we will start with the chiral pool. Chiral pool is chiral pool is the one. In this case, one chiral molecule is converted into another chiral molecule. Here we can see that one chiral molecule is converted into another chiral molecule. Means the starting material or the substrate we use mm, to use to react and form the our desired product are already chiral, and that chiral molecule is changes into our desired product. So if you want any chiral product, we have to start with the chiral starting material, chiral compound. In another case, we will see the chiral auxiliary. Chiral, in this case, the chirality is imparted in the final product by the enantiomerically pure compound which is later removed. It means that uh, any compound, any reaction if we want to induce the chirality in the molecule, first we attach the chiral auxiliary. Means a chiral moiety is attached with that one, and that reaction happens, and the chirality is induced with in the by the influence of this chiral auxiliary, and later after the reaction we remove that chiral auxiliary. In both the cases, we will see that in chiral pool and chiral auxiliary, they are used in equivalent amounts. They are not used in catalytic amount. So for the catalytic amount we use in then there comes the asymmetric catalysis. In asymmetric catalysis, there are three ways to do the asymmetric catalysis: the biocatalysis, transition metal mediated catalysis, and organocatalysis. In biocatalysis, this is accomplished by the Natural catalysts such as enzymes in lipase and this are used. Enzymes are used for the biocatalysis. In transition metal catalysis, what we use the chiral ligands. Chiral ligand gets related with the metal atom, and that metal atom uh, creates reaction with the uh, upper substrate for the desired reaction, and that reaction is guided by the chiral ligands. That chiral ligands induces the chirality in the product. In another, in organocatalysis, the organocatalysis is the two types, that is covalent organocatalysis and non-covalent organocatalysis. The covalent organocatalysis are usually catalyzed by amino catalyst, carbene catalyst, and the Lewis base catalyst, organocatalyst. In covalent catalysis, what happens that the catalyst that has already chiral center or chiral catalyst that binds covalently with the substrate, and then that substrate reacts in influence of the catalyst, that amino catalyst, that catalyst covalently bonded catalyst, and the chiral part of the catalyst introduces the chirality in the substrate, that latter removes and goes into the cycle. In organocatalysis, what happens, we use a Bronsted acid or Bronsted base, that bifunctional catalyst. One part enolizes the nucleophile, other part hold the electrophile, and they bring that electrophile nucleophile in vicinity in a specific orientation, with a specific orientation, so that the attack of nucleophile to the electrophile takes place in a particular direction, and that induces the chirality in the molecule. So for that better understanding, we will see with the example of various examples we discussed here. First, we will go with the chiral pool. In chiral pool, we will see that the lactic acid here, the chiral center is here, the OH, and attached with that chiral center, the lactic acid is converted into L-alanine. Here, how this is happened, the OH is converted to NH2, and this is called used as a chiral pool to synthesize the other chiral compound. Spray. Here, L-lactic acid is first condensed with the benzyl alcohol in benzyl DDC to form the ester, corresponding ester. That ester reacts with PBS3 in I2 in presence of OH is removed by I, via SN2 mechanism with the opposite direction. That 3 is further react with, sorry, that 3 further gets with sodium azide. That sodium azide replaces the I with SN2 mechanism and creates NH3. That NH3 is get reduced with PDCH2 and forms the L-alanine, that we get the final product, desired product. Now we will see that how chiral auxiliary that imparts the uh, imparts the chirality in the molecule. Here we will do the propanoic acid is converted into 5. How this propa means acid chloride is used with a oxazolidinone, oxazolidinone. Oxazolidinone is used as a chiral auxiliary because it is already chiral center is there. This first we attach with the our substrate, this uh, acid chloride is present of butyl lithium, and this acid attachment of this acid chloride with this one, and this nucleophilic center is there in presence of base. This there is acidic proton. That acidic proton attacks on this benzyl iodide to form to remove the iodine and attach it from here. Here what happens that this chiral center is there, that isopropyl group is above the plane, that guides the attack of this benzyl iodide from backside, so that the chirality can be induced, and only backside attack will be favored, and that backside attack will induce the chirality because no upside attack is there, so that the racemic product will be formed. So this backside attack is formed, and then later, after completion of reaction, the in presence of lithium hydroxide and hydrogen peroxide, this oxazolidinone is removed, and we got our desired product. In biocatalysis, we will see that catalyst, biocatalyst enzymes are used. That keto reductase is used to reduce the pro-chiral ketone to chiral alcohol. Here in ketone reductase, the NADPH is attached to it. This NADPH provides hydride ion to this ketone and thus reduces to alcohol, while NADPH DP NADP plus take the hydride from the isopropanol and convert it into ketone. Here the sacrificial isopropanol is used for further production of NADPH, which will reduce the prochiral ketone and give the chiral alcohol. Further, we will move to the transition metal mediated catalysis. Here, we will just discuss about the how metal attaches and reacts with the our uh, substrate. Here, the ligand uh, gets chelated with the metal, and uh, that metal performs all the reactions with the substrate for the oxidative addition, reductive elimination, and that approach of electrophile and nucleophile happens in guidance of this chiral moieties attached with this group. That this chiral group guides the uh, influence and guides the approach of the electrophile and nucleophile, so that in such a way that chirality can be used in the final product. Now we will see that covalent organocatalysis. In covalent organocatalysis, we will understand with one example of iminium catalysis. Like here, one is the can be primary or secondary amine, and this is the chiral center attached with this amine. In this case, if you will, we will use that have alpha proton with aldehyde. That imine condenses with the aldehyde to form the imine, and which tautomerizes to form the enamine. That enamine act as a nucleophile and takes with the electrophile to give the final product. That after removal of the imine, after hydrolysis, you can say of the imine to give the catalyst for the further next cycle. In another case, if you use under alpha beta unsaturated ketone, the iminium forms and that creates the electrophilicity at this beta center. That electrophile can be attacked by any nucleophile or that undergo cycloaddition reactions, and the imine after reaction the imine is removed for the another cycle. Now we will see that non-covalent catalysis. In non-covalent catalysis, we have chosen a specific catalyst like quinine-derived spermide catalyst. Here you can see that this is a tertiary amine that enolizes the nucleophile proton to create the nucleophile, acidic proton to create the nucleophile, and this 2NH group holds the electrophile. The hold of this through hydrogen bonding also increases the electrophilicity of the electrophile. So here what happened, sorry, here what happened that this ketone uh, comes in with hydrogen bonding of this NH proton and in such a way orientation, and this nucleophile diester compound get enolized by this tertiary amine and creates the nucleophile, and uh, these two compounds come in orient in such a way that the attack of this nucleophile to the electrophile takes place either with perfectly with the re phase or with the psi phase, not on the both phases, due to chirality of that catalyst that guides and their static hindrance, that their orientation is such a way that only one phase will get attacked by the nucleophile. And here we can see that the red bond is there at the attack, and the further the product is get removed and the catalyst get free for the another cycle. From this we have uh, come to the know that the how catalysis and how these different types of catalysis are happening in the system, and we use in the lab to create the chiral molecules. From here, I would like to thank everybody, and I would especially like to thank the MMCTT for the Kumaon University Nainital for giving me this opportunity to represent my micro teaching in the refresher course in chemistry. Thank you.